Here I am working through my 2007 algebra-based physics final exam for mechanics. And I'm on problem number 7, just to see how I've changed, see how the problems have changed, see how the physics have changed. So let's just get to this problem right now. I will read it to you because it's a little small. A stunt person wishes to do a loop on a skateboard. Actually, this was from a video. I'm not sure if I saw the video first, but there is a video of a person doing this on a skateboard. He plans, this is where I'd put just the person that plans to start on a ramp to gain speed, so up here, and then go around the loop with a radius of 2.5 meters. So this is r equals 2.5 meters. How high up must the person start so that the person makes it around the loop? How high up above the ground, I guess? See, again, this is an ambiguous thing, but let's call this h. You can assume a point mass, which is important, and that there's no friction. Okay, so this is your classic loop-to-loop problem. So here's the person right there. The person comes down here, and then the person's up here, upside down. So going this way, let's call this V1 equals 0, V2 equals, we don't know, V3 equals, because this is a tough problem, and let's actually work backwards, right? If we're not concerned with time, so that suggests that we should use the work energy principle. So work equals change in energy. I need to declare my system, and it's going to be the skater plus the earth. That means I can have a change in kinetic energy and a change in gravitational potential energy. So if I want to find how fast they're going at these different locations, that's fine. Okay. I could say, okay, well, here's the person up here. There is a normal force on the person that's perpendicular to the direction they travel, so that work done by that 0. Work equals F dot delta R, but if those two are perpendicular, then the work done is 0. So the normal force doesn't do any work. Now, up here, there's actually a trick, right? Because at the top of the circle, you could say, oh, they just need to go, I need to find out how fast they need to go and to get to 0 speed. But if they did that, they would fall. Okay, so you have to be going fast enough such that you're still in contact with the surface of the thing. So up here, I would have this as the gravitational force, and that's the velocity. And so they're moving in a circle, and the acceleration has to be equal to the weight. So let's say at the top, I'm going to say F net y equals negative mg equals negative mv squared over r. Right, so this is the only force acting on them. This is the v squared over r is this acceleration of an object moving in a circle. So that means that's v3 right there. I can solve for what v3 has to be. So v3 has to be equal to, the masses cancel, the negatives cancel. I get the square root of gr. Is that right? G, yeah. So meters per second squared, yeah. So that's the velocity. No. Yeah. That has to be true in order to be still moving in a circle. Now I can use the work energy principle. Now I can say, going from position 1 to 3, work equals 0, and that's going to be the change in kinetic plus the change in potential. So it's going to be K3 minus K1, the kinetic energy, plus U3 minus U1. So now I need to pick where is y equal to 0. Let's pick down here as y equals 0. So that means I get 0 equals K3, which I kind of know, right? Because I can put in my velocity up there. So it's going to be 1/2 m times this squared. So it's going to be gr minus K1. The kinetic energy right there is 0, plus U3. So u3 is going to be mg times this y value. And that's going to be twice the radius. So it's going to be 2r minus u1, which is going to be mgh. And I don't know h. I want to solve for h. Okay, I never said what the mass was. And you'll notice that I can divide everything by the mass. And so that's fine. Now I can just add this to both sides, and I get GH equals 1/2 GR plus 2GR. Is that right? Yeah. So these combined, so that's going to be 4R over 2. So I get 5/2 GR. Divide by H, divide by G, I get, oh, the G's cancel. I get H equals 5/2 R. Huh. So that says that if, yeah, that makes sense. I'm going to leave it like that. I'm not going to get a number just so I don't want to switch to Python. But this says that it doesn't matter if you do this on Mars, right? Because the G canceled. And that kind of makes sense because on Mars, you wouldn't need to go as fast up here, but also you wouldn't accelerate as fast. So because they're both related to the same G, they kind of cancel. It should work on the moon too. And that would be how high you'd be. There was a water slide that did this, and it did a loop. They wanted to do a loop, but it turns out that in order to make the whole thing possible, you want to have this radius small, right? Because you need to start really high up. But if you make the radius small, then you get a really high acceleration, and it turns out that people kind of got hurt, so it was a bad idea. Okay, we got one more problem. I'll do it on the next video. I'll see you there.